Hello, everyone. Welcome to ILTA Physics Online Lectures. Today, I'm going to explain how to represent rotational motion from a kinematics perspective. Generally, the motion of an object moving on a plane can be described using x and y coordinates in a Cartesian coordinate system. However, when we think about rotational motion intuitively, it is often much more useful to represent it by the size of the angle moved around a rotation axis. We call this angular kinematics. What's interesting here is that when we explain the angle of rotational motion, we don't use the degree scale we use in daily life. Instead, we apply a new scale called the radian. While the unit of degrees is more familiar to us, the radian, which originates from the properties of a circle, is a more physics-based scale because it is an inherent geometric characteristic. I'll explain this in more detail in the next section. Today's lecture is about the kinematics of rotational motion, and we'll start with the definition of angular position, which represents the location of an object using an angle. Once the position is determined, we can naturally define velocity. In rotational motion, we call this angular velocity. Finally, looking at the relationship between rotational and circular motion, we will derive the formula relating the angular speed and tangential speed of an object spinning around an axis. Does describing rotational motion, something already familiar to us in daily life, in a physics way feel a bit strange yet? Does it feel like these concepts are just spinning around in your head? Well, let's start catching those spinning concepts one by one and organize them systematically. First, let's briefly summarize what we studied last time. Last session, we have learned the new type of movement called rotational motion. It's the moving but not moving motion. To explain this, we divided the motion of objects in kinematics as follows. The translational motion we've learned so far refers to motion where an object's position changes from one point to another. In contrast, rotational motion is the motion of an object spinning in place around a fixed axis. It's not a change in position, but a change in orientation that defines rotational motion. As an example of an object performing both translational and rotational motion simultaneously, think of an object rolling forward. This is a combination motion where it moves forward while spinning. To explain translational motion physically, the point mass model or particle model is useful because it represents the moving object as a single point, regardless of its size or shape. However, to explain rotational motion, we need a new object model because representing an object as a single point doesn't allow us to describe its rotational speed or direction. Therefore, for the analysis of rotational motion, we need a model that views an object as a collection of many tiny components. We call this the extended body model or the rigid body model. We will learn the detailed analysis methods for the extended body model moving forward. Also, I briefly explained the relationship between rotational and circular motion. As you can see in the diagram on the right, if a fly is sitting on a disc, the fly is performing circular motion along a circular path, but the disc itself is performing rotational motion while staying in place. Lastly, by comparing 2 points on the disc, A and B, we conceptually thought about the difference between angular velocity and tangential velocity in circular motion. All right, now let's describe this rotational motion physically and quantitatively. Let's stop just spinning in place and move forward. Earlier, we learned that circular motion and rotational motion are very closely related. To explain the relationship more specifically, think about the spinning disk example again. When we talk about rotational motion, the object is the entire disk. When we model this object as an extended body and talk about the movement of point A, which is a tiny part of the disk, that movement is circular motion. Think of it this way. A rigid object is just a collection of countless tiny particles, and when the object rotates, every single one of those particles is moving in a circle around the axis. Even if the concept isn't perfectly clear yet, I believe you'll understand it as you keep thinking about it. Now, let's first consider circular motion, which is the motion of a tiny part of a rotating object. Imagine an object moving along a circular path at a constant distance from a center point. Since circular motion is a type of translational motion, let's represent it as a single point on a plane using the point mass model. One way to show the position of this moving object is by using x and y coordinates. However, due to the nature of circular motion, the x and y coordinates at every moment would be very complex and wouldn't intuitively show much meaning. However, if we represent the position of this object using its radius from the center and the angle from a reference line, the expression becomes much simpler and more intuitive. Specifically, since the distance from the center is always constant, we can represent the object's position accurately and simply using only the angle. At this time, if we set the reference line for the angle as the positive x-axis, we define the angle from that x-axis as the angular position. Now let's think about the direction of circular motion. There are only two directions, clockwise and counterclockwise. To use a linear motion analogy, this is like right and left or up and down. For angular position, we will define the counterclockwise direction as the positive direction. As we've seen above, angular position is a vector quantity that has both magnitude and direction. Here we will define a new unit called the radian to represent the angle. Generally, when we talk about angles, we've used the unit of degrees. The concept of degrees is a scale used in daily life where one full rotation around a circle is artificially set to 360. There are various hypotheses as to why ancient people chose 360 specifically, but that's not our focus right now, so I'll skip the explanation. The thing is, degrees are just a unit we use for angles that humans pretty much made up for convenience. It's just that degrees are so familiar to us that they feel intuitive and comfortable. However, the degree scale is difficult to use alongside other units that describe motion, like length and time, making it inconvenient for directly describing an object's movement in kinematics. Therefore, we decided to define an angle as the ratio of the arc length to the radius, and we call that unit the radian. The geometric meaning of the radian unit comes from the geometric properties of a circle. To put it simply, every circle is uniquely defined by its radius, and all circles are similar shapes. Therefore, regardless of the circle size, if the ratio of the arc length to the radius is the same, it always represents the same angle. Also, since a radian is a value obtained by dividing a length by a length, it is a unitless physical quantity. Expressing this as a formula, the angular position theta is equal to the arc length s divided by the radius r. This formula is very important in circular motion, so please make sure to understand and memorize it. If we rearrange this, the arc length can be calculated as the radius times the angular position. Let's relate this new way of notation, the radian, to the degrees we are familiar with. As we know, one full loop of circular motion is called one revolution. In degrees, one revolution is 360. If we express this in the radians we just defined, it's calculated as the entire circumference divided by the radius, which becomes 2 pi. Therefore, 360 degrees equals 2 pi radians. Approximately, 1 radian is 57.3 degrees, or roughly 60 degrees. So, to wrap things up, it's much easier to describe where an object is in circular motion by using its angular position in radians, instead of dealing with messy x and y coordinates. Also, using radians as the unit for angles is much more convenient for using physics formulas than the degrees we use in daily life. Alright, now that we've defined how to pinpoint an object's position in circular motion, what do you think comes next from a kinematic perspective? Previously, we represented the position of an object in circular motion using angular position. The angular position is the angle from the positive x-axis, and its unit is the radian. Now, since the position of the object in circular motion is defined, we can define another parameter for describing motion: velocity. As we've already learned, velocity is the change in position or displacement divided by the time interval. Specifically for circular motion, we can calculate this by dividing the change in angular position by the time interval, and we define this as angular velocity. A change in angular position is the value obtained by subtracting the initial angular position from the final angular position, which can be understood as the same concept as displacement in linear motion. One thing to be careful about here is that angular velocity is the displacement divided by time. Please understand clearly that it is not the arc length or distance divided by time. Just like angular position, we define the counterclockwise direction from the positive x-axis as the positive direction for angular velocity. Therefore, a negative angular velocity means the object is rotating clockwise. One more thing to add. Previously, we analyzed circular motion from the perspective of centripetal force, the cause that makes the trajectory a circle. In physics terms, that is kinetics, represented by Newton's second law, F equals ma. However, today we are looking at the movement of the same circular object from the perspective of kinematics, analyzing the relationships between position, displacement, and velocity. Lastly, let's take a moment to think about the relationship between angular velocity and the object's actual moving speed. The image on the right is a top-down view of a spinning helicopter propeller. The angular velocity of each rotating blade can be calculated as one single value using the formula above. However, if you look at a single blade, point A at the very tip and point B in the middle aren't actually moving at the same speed. Let's look at the velocity relationship between the angular velocity of rotational motion and the circular motion of each part of the object in detail in the next section. Generally, if the direction of a rotating object's angular velocity isn't important, we call only the magnitude of that angular velocity angular speed and denote it as omega. In other words, angular speed is defined as the magnitude or absolute value of angular velocity. If we express this angular speed using other parameters of circular motion, period t and frequency f, it looks like this. Since the period is the time it takes to complete one full circle, based on the definition of angular speed, it can be calculated as the angular position of one full circle divided by the period. Also, since frequency is the reciprocal of the period, we can rewrite it using frequency as follows. Finally, let's derive the relationship between the angular speed of a rotating object and the actual moving speed of the circular motion of its parts, called the tangential speed. Here, we assume the rotating object is in uniform rotational motion with a constant angular speed. Whether it's linear or circular motion, we define speed as the distance moved divided by time. In the case of circular motion, the distance for one full turn is equal to the circumference, and the time for one full turn is the period. So the speed in this case is as follows. If we express this formula using frequency, it looks like this. Now, since we just defined angular speed, omega, this way in the previous equation, the tangential speed of an object in circular motion can be calculated as angular speed times the radius. This formula is very important for expressing the relationship between linear or tangential speed and angular speed. Alright, with that in mind, let's take another look at the rotating disk we were talking about earlier. As shown in the diagram on the right, let's consider the angular speed and tangential speed of 2 points, A and B, on a rotating disk. Since the 2 points are on a same straight line from the rotation axis, meaning they are in the same relative position as the helicopter propeller, the angular speed of the 2 points is identical. But in reality, the speed at which each point travels in its circular path called the tangential speed, is, as we know, faster for A than for B. This is because the radius from the rotation axis to point A is longer than the radius to point B. Notice how, according to this formula, the tangential speed is actually proportional to the distance from the center. This physical phenomenon is the same principle as why we feel a faster speed when we sit on the outer edge of a spinning amusement park ride. Now we are able to explain this quantitatively and accurately using the formula above. That's it for today's lecture. You did a great job during this long session. I'll see you all again in the next lesson.